In this video cast, we'll take a look at some miscellaneous concepts dealing with gases. We'll look at molar volume, volume stoichiometry, how we get R that we use in PV equals nRT and what R is, where we get the density equation for gases, and lastly, some differences between ideal and real gases. During this video cast, you'll need a paper, pencil, and a calculator. Pause the video now so that you have those materials in front of you. First, let's look at molar volume. If you remember from our past study of moles, the word molar, which ends in R, always means per mole. Per mole. And since it's molar volume, it always means the amount of gas volume per 1 mole of gas. And so in terms of units, it would be how many liters are there in 1 mole of gas, or liters per mole. This is known as the molar volume. And it turns out that since we treat all gases the same, whether it be hydrogen, nitrogen, helium, neon, argon, the molar volume that we will calculate is true for any volume of gas, any kind of gas. First of all, let's take a look at the molar volume at standard temperature and pressure, STP. If we do this, we can assume this data. We can assume that pressure is equal to 1 atmosphere. The volume is the thing we want to find. We have 1 mole of gas, because remember we're looking at the molar volume, how much 1 mole of gas occupies. The universal gas constant for atmospheres, and the temperature. The standard temperature, remember, for gases is 273 Kelvin. Putting this into the PV equals nRT equation then allows us to say that V is equal to nRT divided by P. If we plug in the numbers for this, and I'll do it down below here, volume is equal to 1 mole times R, which is 0.08206 liters, times atmospheres per mole times Kelvin, times T, which is 273 Kelvin. Notice our Kelvins cancel with our Kelvin, and our moles cancel with our moles. And then we divide this by our pressure, and our pressure is 1 atmosphere. Notice our atmospheres cancel with our atmospheres, and our units end up being liters. Take a moment right now and plug this into your calculator. You can see that the ones end up canceling out, and if you take 0.08206 times 273, you end up with a number pretty close to 22.4. This is known as the molar volume. And notice in this problem, we didn't identify what kind of gas it was, whether it was nitrogen, hydrogen, helium, neon. We just said that it was a gas at standard temperature and pressure, which means that this molar volume right here holds true for any gas as long as it's at standard temperature and pressure. Any gas at standard temperature and pressure occupies 22.4 liters, and you should memorize this number and know where it comes from. Now, there could be a molar volume for a gas at a different set of conditions, a different pressure, a different temperature, or a different number of moles, of course, but then it wouldn't be called molar, because molar means per 1 mole. But this is the standard temperatures and pressures molar volume, 22.4 liters. Well, taking a look at this ideal gas equation, some people say, well, where do you get this thing called R, that is the ideal gas constant? Let's look at that a little closer. So, what is R? Make sure you're writing this down on your note paper. Well, R is called the ideal gas constant, and how do we get it? How do we get it? Well, it is the constant that relates pressure times volume to moles times temperature. To moles times temperature. And if you look at the equation, PV equals nRT, and we assume 1 mole of gas at standard temperature and pressure, We assume 1 mole of gas at STP. Then we can use this to help solve for R. Let's use the molar volume that we just talked about. That 1 mole of any gas at standard temperature and pressure is equal to 22.4 liters. And let's solve this equation for R. If we do this and rearrange the equation, R is then equal to PV divided by NT, dividing both sides by NT up here. And if we plug in the pressure, standard pressure is 1 atmosphere. The molar volume, the volume of 1 mole of gas, any gas at standard temperature and pressure, which we just solved before, that's approximately 22.4 liters. Divide this by our number of moles, which we're assuming is 1 mole, and then multiplying it by standard temperature, which is 273 Kelvin. Remember, the temperature always has to be in Kelvin. We now get our standardized units for R, which is liters, atmospheres per mole Kelvin. And if you multiply these together and you divide 22.4 by 273, you'll end up with 0.08206 liters times atmospheres per mole times Kelvin. Now, you might wonder, yeah, but there are other values for R. Remember, R is also equal to 8.31, and then R is also equal to, at times when we use it, 62.4. Why do we have 3 different values for R? Well, it all comes down to the units. Remember, we used atmospheres for pressure. Well, what happens if we use the standard pressure in kilopascals? 101.3 kPa. Now the units will be 8.31, and the units would be kPa times liters per mole times Kelvin. Notice the difference is that the pressure units are changed. And this would be for mummy hugs, or millimeters of mercury times liters per mole times Kelvin. So depending on which units you use, atmospheres, kilopascals, or millimeters of mercury, your universal gas constant will be different. These gas constants are given to you on the equation tables when you take the AP test, so you don't necessarily have to memorize them, but you become so familiar with them that you kind of know what they are. Next miscellaneous item is taking a look at gas-gas stoichiometry problems, where we start with a gas and we also end with an amount of gas. In this problem, we're told that we have 10 liters of hydrogen and it reacts with an excess of nitrogen. How much NH3 is produced? And we'll assume it's at STP, even though this really doesn't happen at STP that much. The balanced chemical equation, N2 plus 3H2 goes to 2NH3. As we would with any stoichiometry problem, step number 1 would be writing the balanced chemical equation. Step number 2 then would be converting to moles. And so we need to take our 10 liters of hydrogen and convert it to moles. Now, if you were paying attention just a little bit ago, we know that 1 mole of any gas at standard temperature and pressure is equal to 22.4 liters. So I could take my 10 liters of hydrogen gas, put a multiply sign, put a line, and I could put 22.4 liters on the bottom and 1 mole of that gas on the top. Step number 3 then is the mole-to-mole ratio. Mole-to-mole ratio from the balanced chemical equation. And since I want to know NH3 and I know H2, I put H2 in a position where it's going to cancel, and NH3 is my new set of units. And the ratio is 2, because there's 2 in front of the NH3, to 3 for H2. Step number 4 is, of course, to convert to the asked for units. And in this case, the asked for units are liters once again. And since it takes place at standard temperature and pressure, 1 mole of any gas, in this case NH3, occupies 22.4 liters. And now you math folks are jumping up and down saying, look what happens. Well, since step 2, converting to moles, and step 4, converting back to the asked for units, are the reciprocal of each other, you can notice that the 22.4s and the moles actually cancel each other out. And this is true for any gas-gas stoichiometry problem. You can skip step 2, and you can skip step 4, and you can just take the volume and multiply it by the mole-to-mole ratio in the balanced chemical equation. So if you ever see a problem, and you've seen several of them in your homework already, where there's a volume given and they're asking for a volume in the end, here they're asking how much, in this case liters, of NH3 is produced, well, then just jump right away to the mole to mole ratio, because you can assume that these two cancel out as long as the conditions remain the same. If the conditions change, of course, then you need to use PV equals nRT to find the number of moles. And you could once again use PV equals nRT to convert back to the asked for units, whether it be volume, or there are many times in this step where they want to know the mass of the gas. Then of course you'd use the periodic table to do this. So 10 times 2 divided by 3, ooh, 20 divided by 3. Well, I guess you're going to get close to about 6 1/3 or something like that. So 6 point something liters would be your answer. Let's take a look at another miscellaneous idea in gases, and that's gas density. Remember from a long time ago that density is equal to mass divided by volume, and this is our density triangle. If we want to know density, cover up the D, and it equals M divided by V. Now, if we take this density idea and put it into PV equals nRT, we can actually rearrange this equation to solve for density. Remember, density is equal to mass divided by volume, and if you look at PV equals nRT, we can rewrite it this way, where PV is equal to mass divided by molecular mass that we get from the periodic table times R times T. If we rearrange this equation now by dividing both sides of the equation by V, and then on this side of the equation multiplying by molar mass over RT, which I would have to do over here as well, molar mass divided by RT. Notice my molar masses cancel, my RTs go away, and over here I lose my volumes, and I'm left with mass divided by volume. Mass divided by volume, remember, is equal to density. So my mass divided by volume here can be replaced by the letter D, and this is equal to molar mass, I'm just going to write capital M there, times pressure divided by RT. Military police divided by rapid transit is equal to density. This equation is not given to you on the equation sheet that you get during an AP exam, and so you either need to be able to derive this, or you can simply remember that the equation is MP divided by RT is equal to the density of any gas. That's where that equation comes from. Last miscellaneous item for gases is looking at the difference between real and ideal gases. And you may have watched a video cast about this already or heard a talk about real versus ideal gases. And we assume almost entirely throughout this chapter that all gases are ideal. And an ideal gas assumes two very important things. First of all, it assumes that the molecules of gas that make up the gas occupy no volume. Now, the gas itself occupies a certain volume, but we assume that the molecules that make up that gas have no volume themselves, which sounds like a contradiction, and it is, but it's one of the assumptions we need to make a gas be ideal. Well, what about real gases? Well, they actually have some small amount of volume, which probably makes sense that they actually do. But we don't take that into consequence when we look at PV equals nRT and the other types of equations that we use. The second thing we assume for an ideal gas is that molecules of gas have no attraction to one another. Molecules of gas have no attraction to one another. Well, as you probably know, they actually do attract. Maybe not very much, but they do attract just a little bit to one another. And these two consequences, that they actually have some small amount of volume and that they actually do attract, can sometimes cause problems for gas equations or gas calculations. So, what conditions cause us to be more like a real gas than an ideal gas? Well, think in terms of phase change. Remember, we're always talking in terms of gases, and gases would exist when it gets hot, and it would also exist when they're not pressurized very much. And so if you undertake conditions that are very, very low temperature, very low temperature, this causes a lot of issues, because then you take and you're going to go from a gas to a liquid state, and of course PV equals nRT and other assumptions we make about gases aren't true for liquids. And so low temperature causes things to become more real than ideal. And secondly, at really high pressures cause us to take those gas particles and squish them really close together. When you squish them close together, there's more attraction to these particles. And of course they might start to take up more volume too, or we might have to consider the volumes of these particles as well. And so the gas also, once it's squished, starts to become a liquid again, just like we talked about here. So gases become more real at very low temperatures and at really high pressures because they're no longer gases anymore. And those are our consequences, or those are the two things we need to look for to find out when gases deviate from ideal conditions. Now there are equations that help deal with that. One of them is the van der Waals equation that we learned about in a different video cast, where we take into consequence these attractions and we take into consequence some of these small volumes. And that equation, remember, is that P is equal to nRT divided by V minus NB minus n squared A over V squared. And this corrects for the molecular attraction. And this portion right here, actually this bottom part right here, corrects for the volume that molecules actually have. And of course it's unique to whichever type of gas that you're using, because different molecules of gases take up different volumes, and different types of gases have different attractive characteristics. And that's where the A and the B come in. They're unique for each type of gas. So those are some miscellaneous gas consequences that you should be familiar with. Some of them perhaps you already knew. Some of them might be very new to you as well. But take a look back if you don't understand molar volume, how much volume 1 mole of gas occupies, especially at standard temperature and pressure, where R comes from and PV equals nRT, how a volume stoichiometry problem can actually be really easy because you can ignore that part where you convert to moles or convert back, and the differences between real and ideal gases.